Well, let me tell you about one of the strangest facts in all of physics. Light travels at exactly 299,792,458 meters per second in a vacuum. Not approximately, exactly. So exact that since 1983 we don't even measure the meter anymore. We define it based on this speed. 1 meter is the distance light travels in 299,792,458 of a second. Think about that. We've stopped measuring the speed of light and started using it to measure everything else. And that number, that very specific number, is not just about light, it's about the structure of space-time itself. It's a conversion factor between space and time, like how you convert inches to centimeters. Except this conversion factor determines how the universe works at the most fundamental level. Now, here's what most people want to know. Why? Why the speed? Why not faster? Why not slower? And more importantly, why is there a speed limit at all? Why can't you just keep accelerating something faster and faster indefinitely? You put more energy in, it goes faster. Put in more energy, faster still. What's stopping you from eventually pushing something past the speed of light? The answer is going to seem strange. The speed limit exists not because of light, but because of causality, because of time itself, because of the way space and time are woven together into a single fabric. And understanding why nothing can go faster than light means understanding something profound about the shape of reality. Let me tell you what happened in the late 1800s. Physicists were trying to measure the speed of light with increasing precision. And there was this idea, this theory that everyone believed, that light was a wave moving through something called the luminiferous ether, an invisible substance that filled all of space. Like sound waves move through air, light waves were supposed to move through this ether. Now, if that's true, then Earth must be moving through this ether as it orbits the sun, which means there should be an ether wind. And if there's an ether wind, then light should travel at different speeds depending on which direction you measure it. With the wind, against the wind, perpendicular to the wind, different speeds. In 1887, two physicists, Albert Michelson and Edward Morley, built an extremely sensitive experiment to detect this. They split a beam of light, sent the two beams in perpendicular directions, bounced them off mirrors, and brought them back together. If light traveled at different speeds in different directions, the beams would arrive at slightly different times, creating an interference pattern. They found nothing, no difference. Light traveled at exactly the same speed in every direction they measured. They tried the experiment at different times of year, when Earth was moving in different directions. Same result, no difference. This was bizarre. Think about it in ordinary terms. You're in a car driving at 60 miles per hour. Another car is driving toward you at 60 miles per hour. You're approaching each other at 120 miles per hour. Velocities add. That's how motion works in everyday experience. But light doesn't work that way. If you're flying through space at half the speed of light and you shine a flashlight forward, that light does not travel at 1.5 times the speed of light. It travels at exactly the speed of light, the same speed it would travel if you were standing still. And if you fly toward a beam of light at half the speed of light, it still approaches you at full light speed, not 1.5 times light speed. Velocities don't add at high speeds the way intuition suggests, and Einstein, very brilliant fellow, took this seriously. In 1905, he built an entire theory on this one fact. The speed of light is the same for all observers, regardless of their motion. This is called the principle of relativity. And if the speed of light is constant for everyone, then everything else has to change. Time, length, mass, even the concept of simultaneity. You see, if light speed is constant, then time must be flexible. Here's what I mean. Imagine you're on a spaceship traveling at 86.6% of the speed of light. There's a clock on your ship. From your perspective, sitting on the ship, the clock ticks normally, 1 second per second. But someone watching you from Earth sees something different. They see your clock ticking at half speed. What takes 1 second on your clock takes 2 seconds on theirs. This is called time dilation. And it's not an illusion, it's not a trick of perception. Time genuinely passes more slowly for moving objects. At 99.5% of light speed, time slows down by a factor of 10. What takes 1 second for you takes 10 seconds for someone watching you. Approach light speed and time nearly stops. We see this every day in particle accelerators. Muons are subatomic particles created when cosmic rays hit the upper atmosphere. They're unstable. They decay in about 2.2 microseconds when they're at rest. That's their lifetime. In 2.2 microseconds, traveling at 99.94% light speed, a muon should travel only about 660 meters before decaying. But the atmosphere is 10 kilometers thick. These muons should decay long before they reach the ground. Except they don't. They reach the ground all the time. Why? Time dilation. From the lab frame, the muon's lifetime stretches to about 64 microseconds because it's moving so fast. Time slows down for the muon. From the muon's perspective, its lifetime is still 2.2 microseconds, but the atmosphere is length contracted to 660 meters. Either way you look at it, the muon reaches the ground. Special relativity predicts this. Experiments confirm it to extreme precision. And here's where it gets really interesting. As you go faster, not only does time slow down, but lengths contract in your direction of motion. At 86.6% light speed, lengths shrink by half. At 99.5%, by a factor of 10. Approach light speed and the entire universe in your direction of travel compresses to nearly zero thickness. But there's something else, something even stranger. As you accelerate, you get heavier. Not in the sense that you gain more atoms, in the sense that it becomes harder and harder to accelerate you further. Your inertia increases. Now, in Newtonian mechanics, kinetic energy is 1/2 mv squared. Mass times velocity squared divided by 2, double the speed, quadruple the energy. Simple, but that formula only works at low speeds. At high speeds, you need Einstein's formula. Kinetic energy is gamma minus 1 times mc squared, where gamma is 1 divided by the square root of 1 minus v squared over c squared. And here's the thing. As v approaches c, as your speed approaches the speed of light, gamma approaches infinity. It diverges. The energy required to accelerate you further increases without bound. Let me show you what this means. To accelerate an electron to 99% of light speed takes a certain amount of energy. To reach 99.9% takes about 10 times more energy. To reach 99.99% takes another 10 times. Each additional 9 in that percentage costs exponentially more energy. To reach exactly light speed would require infinite energy. The universe doesn't have infinite energy. Therefore, nothing with mass can reach light speed. It's not that there's some barrier you hit, it's that the speed of light is an asymptote. You can get closer and closer, but you never actually get there. At CERN, the Large Hadron Collider accelerates protons to 99.99999, 1% of light speed. Each incremental increase toward light speed costs exponentially more energy. They're pushing protons to within a hair's breadth of light speed, and it takes the combined energy output of a small city to do it. To go faster would require even more. To reach light speed exactly would require infinite energy. Think about that. The universe has a built-in speed limit not because something is blocking the way, but because the structure of spacetime itself makes it impossible to reach. Now, you might ask, if nothing can reach light speed, why does light travel at light speed? Good question. The answer is that photons, particles of light, have zero mass, no mass at all, and the equation relating energy, momentum, and mass is E squared equals pc squared plus mc squared squared. Energy squared equals momentum times light speed squared plus mass times light speed squared squared. For a photon, m equals 0, so E equals bc. Energy equals bc. Energy equals bc. Energy equals momentum times the speed of light. A photon has energy and momentum but no rest mass. And here's the thing. A massless particle must travel at exactly light speed in all reference frames. It can't slow down, it can't stop. Stopping would mean zero energy, which for a massless particle means non-existence. This is why the speed of light is the same for all observers. It's not that light is special, it's that massless particles must travel at the invariant speed c. If you discovered tomorrow that photons actually have a tiny mass, they'd travel slightly slower than c. The so-called speed of light would be a misnomer. What we call the speed of light is really the speed of causality, the maximum rate at which information or influence can propagate through spacetime. You see, the speed limit exists to preserve cause and effect. If information could travel faster than light, different observers in relative motion would disagree on the order of events. One observer sees event, a cause event, B. Another observer, moving relative to the first, sees B happen before A, sees B cause A. You could send a signal into your own past. Create grandfather paradoxes. See an effect before its cause. Special relativity says events separated by what we call space-like intervals, events that are farther apart in space than light can travel in the available time, have no definite temporal order. Different observers disagree on which happened first. Only events separated by time-like or light-like intervals, events within the light cone, have an observer-independent order. Everyone agrees on their sequence. The speed limit protects causality. Allow faster than light travel, and you allow time travel. You allow logical contradictions. You allow effects without causes. The universe forbids it not by force, not by some cosmic police officer enforcing a law, but by geometry. Space-time is structured so that faster than light paths simply don't exist, any more than a path north of the North Pole exists. There is no north of the North Pole. There is no faster than the speed of causality. And you know what? The speed of light, c, appears everywhere in physics. Not just in electromagnetism, not just in optics, but in relativity, quantum mechanics, thermodynamics. It's the conversion factor between energy and mass. E equals mc squared. Energy equals mass times the speed of light squared. That c is the same c, the speed of causality. It's the ratio of electric and magnetic field units. In the equations of electromagnetism written down by James Clerk Maxwell in the 1860s, this speed appears naturally. Maxwell calculated it from purely electromagnetic considerations and got 298,000 kilometers per second, very close to the measured speed of light. And he realized these are the same thing. Light is an electromagnetic wave. It's the speed of gravitational waves. In 2015, the LIGO collaboration detected gravitational waves from colliding black holes, ripples in space-time itself, traveling at exactly the speed of light. Because gravitational waves are carried by gravitons, which like photons are massless and must travel at c, it's the speed of all massless particles. Photons, gravitons, gluons, if they were free, which they're not, but theoretically. Any particle with zero rest mass travels at c, not because c is the speed of light, but because c is the speed of massless particles, the speed of causality, the conversion factor in the geometry of space-time. Richard Feynman, very brilliant fellow, said it best. The speed of light is not about light. It's about the structure of space and time. And he was right. Every limit reveals a deeper structure. Speed limits on highways exist because cars have mass and momentum and braking distances. The speed limit of the universe reveals that space and time are not separate, that causality is geometric, that the fabric of reality has a built-in maximum rate of change. You can't exceed it because it's not really a speed. It's the shape of existence itself. It's the rate at which now becomes then, the rate at which here becomes there. The fundamental exchange rate between space and time. And here's something practical. GPS satellites orbit Earth at high speed. Time dilation affects them. Their clocks run slightly slower than clocks on Earth because they're moving, but they're also higher up where gravity is weaker, and general relativity says time runs slightly faster in weaker gravity. The two effects partially cancel, but not completely. Without correcting for relativistic time dilation, GPS would accumulate errors of about 10 kilometers per day. Your phone's map would be off by 10 kilometers after 24 hours. We have to program the satellites to account for the fact that time passes at different rates depending on motion and gravity. This is not theoretical, this is not abstract philosophy, this is engineering. We build machines that depend on the fact that time is flexible, that the speed of light is constant, that space-time is curved. And they work. Now, people sometimes ask, what if we found a way around it? What if we found a loophole? What if we could warp space-time, create a bubble, travel through a wormhole? Well, general relativity does allow for some strange solutions. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a theoretical way to achieve faster-than-light travel by contracting space-time in front of a ship and expanding it behind. You're not moving through space faster than light. Space itself is moving, like a surfer riding a wave. The surfer isn't moving faster than the wave. The wave is carrying the surfer. But there are problems. Big problems. Creating an Alcubierre bubble would require exotic matter with negative energy density. We've never seen such matter. It might not exist. Even if it does, the energy required might be equivalent to the mass energy of an entire planet or a star. And there are causality concerns. You could still use it to send signals into your own past, creating paradoxes. Wormholes, shortcuts through space-time, face similar issues. General relativity allows them mathematically, but keeping a wormhole open long enough to travel through would require enormous amounts of exotic matter. And again, causality problems. Traversable wormholes might allow time travel. The universe seems very insistent on preventing violations of causality. Every time we find a mathematical loophole, we discover it requires something that probably doesn't exist, or energies we can't possibly achieve, or it creates logical contradictions. And you know what? I think that's beautiful. The universe is consistent. Causality is protected. The structure of space-time is coherent. And that structure imposes limits. The speed of light, c, is one of those limits. Not an arbitrary rule, but a fundamental constant defining the geometry of space-time. Think about what this means. Every time you turn on a light, you're interacting with particles that must travel at the cosmic speed limit because they have no mass. Every time you look at a star, you're seeing light that has traveled for years, decades, centuries at exactly 299,792,458 meters per second. Not a little faster, not a little slower. Exactly that speed, because that's the speed of causality. When you use your phone's GPS, you're relying on corrections for relativistic time dilation. Your phone knows that time passes at different rates for satellites moving at different speeds and different altitudes. It accounts for the fact that the speed of light is constant for all observers and that space-time is not rigid. The universe has a speed limit, and that limit reveals something profound. Space and time are not separate. They're woven together into a four-dimensional fabric called space-time. And that fabric has a structure, a geometry, a set of rules. The speed of light, c, is not a speed limit in the sense of a maximum velocity, it's a conversion factor. It's the rate at which space converts to time, and time converts to space. It's the invariant speed, the speed at which all massless particles must travel, the speed at which causality propagates. You can't go faster than light, not because something will stop you, not because you'll hit a wall, but because faster than light doesn't mean anything. It's like asking what's north of the North Pole. The question assumes a framework that doesn't exist. There is no north of the North Pole. There is no faster than the speed of causality. And that, I think, is one of the most beautiful things in physics. The universe is not arbitrary. It has a structure. And that structure is mathematical, geometric, elegant. The speed limit of the universe is not an inconvenience. It's a window into the deepest nature of reality. Every limit reveals a deeper structure. The speed limit of the universe reveals that space and time are not separate containers in which events happen. They're a single unified fabric. They're space-time. And the rate at which you can move through space affects the rate at which you move through time. Move faster through space, and you move slower through time. Approach the speed of light, and time nearly stops. Photons, massless particles of light, experience no time at all. From a photon's perspective, if it had a perspective, it's emitted and absorbed in the same instant. No time passes. The journey from the sun to Earth, 8 minutes for us, is instantaneous for the photon. And here we are, made of particles that do have mass, moving through space-time at speeds far below c, experiencing time at a rate determined by our motion and the gravitational field we're in, trying to understand the structure of the universe, trying to understand why there's a speed limit at all. The answer is not that the universe is lazy or stingy with energy. The answer is that the universe has a geometry, and that geometry determines what's possible and what's not. Faster than light travel is not impossible in the sense of being very difficult. It's impossible in the sense of being geometrically incoherent, like a square circle. The words sound like they mean something, but they describe a logical contradiction. The speed of light is the speed of reality itself. It's the maximum rate at which change can propagate, the maximum rate at which cause can become effect, the maximum rate at which information can travel. And that maximum is not arbitrary. It's built into the structure of space-time. And you know what? We've tested this over and over. In particle accelerators, we accelerate particles to within a fraction of a percent of light speed. We've measured the lifetimes of unstable particles at high speeds and found exactly the time dilation predicted by relativity. We've sent atomic clocks on airplanes and found they disagree with clocks on the ground by exactly the amount predicted. We've detected gravitational waves traveling at exactly the speed of light. Every test confirms it. The speed of light is constant. Time dilation is real. Length contraction is real. The universe has a speed limit, and that limit is fundamental. This is not some theoretical idea we think might be true. This is how the universe works. This is what we measure, what we observe, what we build our technology around. So when someone asks, why can't we go faster than light? The answer is not, we don't have powerful enough engines. The answer is, the question doesn't make sense. Faster than light for anything with mass would require infinite energy. And even if you had infinite energy, which you don't, which the universe doesn't, you still couldn't do it, because the structure of space-time doesn't allow it. The speed of light is not a barrier, it's a conversion factor. It's the shape of space-time itself. You can't exceed it any more than you can exceed the number 1 by dividing something by itself. It's not a challenge to be overcome. It's a fact to be understood, and understanding it reveals something profound. The universe is not a collection of objects moving through empty space as time ticks away in the background. The universe is a unified space-time, and the speed of light is the rate at which space-time allows change to propagate. That's it. That's the answer. Not because someone said so, not because of a law written in some cosmic rule book, but because that's the geometry of reality. And that, I think, is beautiful. The universe has rules, deep rules, mathematical rules, and those rules are not arbitrary, they're necessary, they're coherent, they're elegant. The speed of light is one of those rules, and every time you see light, every time you look at the stars, every time your phone finds your location, you're interacting with that rule, with that fundamental structure of space-time. That is how it works. That is the universe, and we get to live in it and study it and understand it. And I think that's wonderful.